Today we're going to start section 3.3. We're going to be taking a look at increasing and decreasing functions and the first derivative test. So the first thing we're going to take a look at is what we mean by increasing and decreasing. So I'm going to give you a couple definitions and I'll draw you some pictures that go with them. A function is described to be increasing if it has the condition that when x1 is less than x2, this implies that f of x1 is less than f of x2. And for decreasing, the same part starts at the beginning the same way. It's x1 is less than x2, but f of x1 is greater than f of x2. That's considered to be a decreasing function. So there's some space in your notes if you've printed them off, kind of like on my screen, where I want you to be able to draw a picture to the right so you can see visually what this is describing. So it says that x1 is less than x2, so it looks something like this. But it tells us the f of x1 value is below, it's less than the f of x2 value, which would be above. So something like this is going on. So here's f of x1, and approximately here, according to my picture, is f of x2. And it has to work for the entire interval. So we can do this for all the points sort of in between x1 and x2. So increasing means it's doing something like this, or something like this, or something like this. You can think of it as you read the graph from left to right, because that's how we always read mathematics as well, as a graph that's going uphill. So this is an increasing graph. And then if I have the same condition to start with on x1 less than x2, but I actually have the f of x1 value bigger than the f of x2 value like this, then I have a decreasing graph. And again, it can be doing like this, it can be going straight, it can be going downhill. What it can't be doing is something like this, right? Because part of that is not actually have values that are, y values are smaller on the left versus on the right. Oh, sorry, a little bit more. Thank you. So no graph like that, I'll redraw it like I could draw it, looks something like this. So this would be a decreasing graph. Okay, so theorems 3.5 and 3.6 actually push us into the second part of the description of the title here, which is the first derivative test. Okay, so let me pause for a second. A few of you are still writing this screen. So everything here in chapter 3 is applications of derivatives. We talked about that when we first started. But one of the applications of derivatives is how we relate first derivatives specifically to whether the graph is increasing or decreasing. And that's what we see happening in our next theorem. Theorem 3.5 tells us that if the derivative is positive, that's what f prime of x being greater than 0 means, then the graph of f is increasing. Number 2 says if the derivative is negative, then the graph is decreasing. And 3 says if the derivative is 0 for an interval, then the graph is constant. Now remember, derivatives are slopes. They're slopes of tangent lines. So we're going to go back to our picture after you've had a chance to write this in and sort of justify how this makes sense from a picture. But jot these down first. Okay, so I'm going to come back over to our pictures that we drew of increasing and decreasing, and I'd like for us to just pick any random point on the first curve. I'm going to mark mine in blue, and we're going to draw a tangent line. So if I drew a tangent line, it'd look something like that. We talked about those in chapter 2, right? What can you tell me about the slope of this tangent line? No. Change the word. It's positive. Okay, so the slope of that line is positive. Agreed? It's a positive slope. That's what this description is on number 1. It says the slope is positive. That's what a derivative is. The slope is positive. And based on the definitions that we have established, this is an increasing graph. And it didn't really matter if I put that blue dot where I put it, or I could have put it somewhere else, right? It could have been over here. And when I drew the tangent line over here, I still have a positive slope on my tangent line. And at every point in between x1 and x2, the graph would have a positive sloped tangent line, right? So it is equivalent to say that the derivative is positive or the graph is increasing. We can do the same picture for number 2. We can take our second graph here and put a random point anywhere you wish it on the graph. And we can draw our tangent line to that point. And anywhere I put that dot, the tangent line is going to have a slope that is negative, right? So a negative slope or a negative derivative is equivalent to having a decreasing interval, or a graph that is decreasing on that interval anyway. Okay, does that make sense? Now, we didn't have a picture for the last one, so I'll kind of sketch something that's happening in here. But if your slope is 0, if your tangent line is 0, that means you have a flat tangent line, right? If the derivative is 0, it means the slope is 0. It means the graph is flat. But the only way to get a graph that is flat is the graph itself is a constant value. So if I drew my grid in, which I didn't do, let me draw it in here. Let's change this. Wow. Try that again. Okay, so here's my derivative graph. Now I drew a red line. The only way that derivative is going to be 0, right, is if I have a constant graph. And everywhere along that line, the derivative would be 0. You can think about it from an equation perspective, right? When we took derivatives of constants, right, the derivative of 5 is 0. The derivative of 7 is 0. Those are horizontal lines. So we've got horizontal pieces of lines, or segments of lines anyway, segments of the graph anyway. Okay, and then the last bit of definition, if you will, this one's a theorem too, but a theorem that we have is this one. So a lot of writing. So listen to what it's saying first, and then I'll let you write it down. Can everybody do that for me? Okay. This is telling you how we decide if we have a maximum or minimum. So the first one says, the last thing highlighted or underlined says local maximum. What a local maximum means is that the graph went from increasing to decreasing. And can you see how that would force you to have a maximum value? Right? This pot right here would be a maximum value. The second one talks about having a local minimum. And it talks about the graph going from decreasing to increasing. And again, we can see that should give us a local minimum value. And if the graph does not change, right? If it's going from increasing and then it's again increasing, even if there's a disconnect, this location where this is happening, even if the disconnect's there, is not a maximum or minimum. Now, it doesn't say what it is. We just know it's not a max or a min. Okay? So go ahead and take a minute to write those down. There's a lot of writing on this slide. Okay, so you might have noticed that there was a phrase. We've talked about it in a previous section of material. The phrase is critical number. All of these locations that are identified as these C values, and the C value is a critical number. A C value is found, or a critical point is found when we find the derivative equal to 0. Okay, so that's what a critical number is. It's some location where the derivative is 0. And that location where the derivative is 0 are these points where we're checking, is it a max, is it a min? So I mention that because that's our first step in trying to use the first derivative test, is that every single time we're going to be taking a derivative, setting it equal to 0, and solving. So you're going to get even better at your algebra skills. That's what this means, right? We're going to do some algebra and trig for that matter. So we're going to do one example, and then we'll pause for today. This is y equal x plus 4 over x, and it would probably be helpful first to rewrite this as x plus 4x to the negative 1. Is everybody good with that? Okay. So every single time we're trying to find if we have increasing and decreasing, or find if we have relative extrema, what we're going to be looking for is taking the derivative, setting it equal to 0, and solving it. That's always our first step. Okay, so we need to take the derivative of x plus 4x to the negative 1. So what's the derivative of x? 1. And what's the derivative of 4x to the negative 1?
Negative 4x.
Yeah, good. You guys are saying it in unison. It's great. Negative 4x to the negative 2. Everybody good with that? Okay. You can leave it written like that if you wish, but I think it might be easier to see what's happening if we rewrite it the way it started. Either option is okay. But our goal is to take that derivative and set it equal to 0 and solve it. Okay? So for starters, I probably want to move the x squared so that it's on the same side, or not on the same side, as the 1. Now you could move the 1 if you want. I'm actually going to move my 4 over x squared just because it's going to make it positive if I do. So I'm going to add my 4 over x squared to the right instead of shifting the 1. How would I solve this? There's more than one option. I could have not even done what I just did, but I think probably this is our best choice. We can multiply by x squared, or you might look at this and say, can I cross multiply? Those are some different phrases that you would have seen before. So we're going to multiply, I'm going to write it this way, multiply it by x squared. If you want to write this as 1 over 1 and cross multiply, that works just as well. So this is x squared is equal to 4. And then we would square root it. So you guys even remember the plus or minus. Good job. So this is plus or minus 2. Everybody good so far? Okay, so there are two critical points, 2 and negative 2. But there's actually one more. So I left this off over here, but I want to go back and rewrite it in. There's one other place that's a critical point. Do you remember what it is? Huh? It has to do with zeros. It does not exist. If the derivative does not exist, it also poses a place that we could have a critical point. At the very least, it may not be a max or a min, but it may be a place where it changes from increasing to decreasing. So over here, we have one more location from right in here. We could actually have 1 minus 4 over x squared is equal to does not exist. Where is that does not exist going to happen? Yeah, this one is at x equals 0. Yeah. So we have 3 critical points, 0 and plus or minus 2. Everybody good? Okay. What we want to know is we want to know what happens in between those places. We know what happens at 2, negative 2, and 0. At 2 and negative 2, I get a derivative of 0. And at 0, I get does not exist. I know what happens on the graph at those specific values. But what I want to know is what happens between them. So what we're going to do is we're going to draw a number line. And my number line needs to include the values that I just identified as being critical points in order. There's no need for there to be a scale to it. I just need to make sure that they're in order. So negative 2 and then 0 and then 2. Everybody good with that? Okay, cool. What we're going to do is we're going to test values in between them, and you can test any value you like. So I might look at this and choose to say, hey, look, a number that's before negative 2 would be negative 3. But you might look at that and say a number that's before negative 2 is negative 5, and either one will work. Doesn't matter what you pick. You need to pick a number on each interval, okay? So we're going to pick numbers on each interval. I'm going to write them in red. I'm going to pick negative 3. There are sometimes nice choices. What's the nicest choice between -2 and 0? -1, right? So there are sometimes choices that are just naturally nice, just like 1 is the nicest choice between 0 and 2. If you really wanted to do 1.5, go for it. It's going to work just fine. But the nicest choice is 1. And then just for symmetry's sake, I'm going to do a 3 over here, but we could do anything bigger than 2 and it would work as well. Okay, pretty good with that. Okay, so what we're going to do then is we're going to take each one of these values, these 4 values, and I want to know what is the derivative doing there. Is the derivative positive or is the derivative negative? And it will be one of the two. It can't be there. I mean, this is an either or thing. It can't be 0, right? It's positive or it's negative. Why can't it be 0? Because I found the 3 places that I have critical points. 2 of them were 0, -2 and 2. It's not 0 anywhere else. Okay, so every single one of those values is going to be either positive or negative. So I take each one of them and I put them into the derivative. Oh, it's called y prime. We'll use y prime. So I'm going to do y prime of 3. How about -3? I'm going to do y prime of -1. I'm going to do y prime of 1, and I'm going to do y prime of 3. And you can let your calculator do that. So if you have a calculator, put the derivative into your calculator. Not the original function, but the derivative that we found. And you can put either version of it into it. So you can either put in this one, or you can put in this one. And you're going to put that into y1. Okay? You can enter this data entry by hand too, but this is kind of a nice way to do it with our calculator. So I'm going to put in 1 minus 4x to the -2. So once that's in y1, so you're storing this in y1, you're going to go into the table, that second graph. Your table should allow you to put values in. We set that up before, but if you didn't have your calculator that day or it's no longer allowing you to put values in, let me know. Okay, the values we're going to put in are the ones that are listed here. -3, -1, 1, and 3. And it's going to spit out some values for you. We don't really care what the number is it spits out. We care whether it spits out a positive or a negative. Does that make sense? So when you put in -3, what did your calculator give you? A positive or a negative? A positive. What about at -1? Did it give you a negative? Sorry, I put something in my calculator wrong, but my paper says negative, so you're right. How about at 1? Oh my goodness, I heard both things. Which one was it?
Negative.
It's negative. And how about at 3? Positive. Okay. So in terms of the graph, remember positive, so I'm going to put them up here, positive, negative, negative, positive. Positive means it's going uphill. Negative means it's going downhill. So this is the graph's image in general that I'm looking at. It's going uphill, downhill, downhill, uphill. You might be thinking, well, how can it go downhill and then break and go downhill again? And the reason that's happening, and if you looked at the original graph, you'd see it too, but is because this was the does not exist point at 0. There's an asymptote there. That's actually why that's happening. So don't let that concern you, but just be aware that that is what's happening. So our question actually asked us about increasing versus decreasing. So that's the answer that we're looking to find here. And I'm kind of out of space, so let me shift this over. So the graph is going to be increasing at the positive places. So that's -infinity until we get to -2. It's not just increasing at -3, right? It's an interval. You picked -3, I picked -3, but we could have picked -5 just fine, right? It's everything in this space that it's increasing on. And then we jump over here and it's increasing again from 2 to infinity. So you'll see a U for union here, and then it's 2 to infinity. And then it's decreasing in the middle pieces. So I can't just put -2 to 2 because it stops decreasing at 0. So it is -2 to 0. Notice there are parentheses here. Union 0 to 2. Okay, it breaks and it stops at 0, and it starts back at 2. Also notice that even though we sort of have intervals that seems like we could sort of do, it's all parentheses, right? We're only increasing on open intervals, decreasing on open intervals. So they're always going to be parentheses. So whether it's an infinity or a number, it's an open parenthesis, okay? All right, we'll pick back up with example 2 next time.